Let's talk about nuclear chemistry. So, to start with, we need to discuss the discovery of radioactivity. So, Henri Becquerel studied phosphorescent uranium compounds in 1896 and accidentally discovered X rays. And he wasn't exactly sure what was going on. And he had some ideas, but he wanted to seek the advice of Marie and Pierre Curie, who were amazing scientists of their time. Each of them won the Nobel Peace Prize, or not peace, Nobel Prize for Science. Marie Curie concluded that a nuclear reaction was taking place to cause the emission of X-rays. And the spontaneous emission of radiation by an unstable atomic nucleus was the radioactivity. That is the term that was coined during that time. So, nuclear chemistry, we had we had this experiment that happened. You had a lead shield box, and in that lead shield box was a radioactive material. And you shot that beam of particles through, and it went through this little slit in the lead, and it was aimed in between two electrically gold charged plates. Now, they noticed what happened whenever they had a photographic film, and they noticed that some particles were deflected from the negatively charged plate and they landed over here. And then you had some particles that were deflected from the positively charged plate and they landed over here. And then you had some particles that weren't affected at all and just went straight through. So they noticed these three areas on their photographic film. And so they were thinking, like, what does this mean? Well, they knew that like charges repelled like, and opposite charges attract. So the particles that were attracted to the negative and repelled by the positive, they must have a positive charge. The particles that were repelled by the negative and attracted to the positive must have a negative charge. And then the particle that wasn't affected must not have a charge at all. Now, nuclear notation. So now they know that there are three different particles, alpha, beta, and gamma. They don't necessarily know what they are at this point, but this gave them a starting point. And then they realized that beta particles have a very tiny mass. They're comparable to electrons. And the positive particles are much bigger. And since they were deflected less than the negative particles, they must have a larger mass. They've discovered that actually these alpha particles have the same mass as a helium nucleus. And then they realized that in addition to having no charge, alpha or gamma rays actually have basically no mass. So it's quite interesting. And they began to think, how do I write this? So, nuclear reactions involve the protons and neutrons found in the nucleus. They don't involve the electrons at all because these are nuclear reactions. Everything that is happening within the nucleus itself to the protons and the neutrons decaying or absorbing another particle. If particles involve electrons, then they're chemical reactions. So these only are in the nucleus. And they said, well, how do we show nuclear notation? So then we look at it this way. We say, well, we have the chemical symbol. So example, if we have uranium, you put the mass number up here and say that's 298. And then the atomic number, which is the number of protons, you put down here. So chemical symbol, mass number, number of protons. That's how we write nuclear notation. Now, when you write the nuclear notation or equation, it's important to indicate which isotopes of the given elements you're dealing with, because some are naturally radioactive and some aren't. And so by writing the notation, you can guess what the products are going to be. So whenever you have radioactive decay, it's the release of radiation by radioactive isotopes. And that is what's called decay. The nuclei of radioisotopes are unstable. Nuclei is a plural of nucleus. Now, there are three types of nuclear radiation. You have alpha, beta, and gamma rays. We're going to talk about each one in detail. Alpha particles are helium nuclei consisting of 2 protons and 2 neutrons. That's why I said the weight is comparable, or the mass is comparable to a helium nucleus. So they're quite large. They're the largest of the 3. Now the mass number goes down by 4. If you look, this is just basically math. You have 226, radium 226. So we have 88 protons, 226 is our atomic mass, and it decays into an alpha particle and radon 222. It is just a math problem. This is a total. The total has to be 226 for your top superscript. So 4, we know, is the alpha particle. So 226 minus 4 gives us 222. 88 is our subscript. We know that an alpha particle has 2 protons. So the total of the products has to equal this atomic number. So 2 plus 86 equals 88. So in an alpha decay, the mass number always goes down by 4. The atomic number always goes down by 2. You still have the same number of nucleons on both sides. We've just rearranged them. Remember, law of conservation of mass. We have to follow the law of conservation. Now with beta decay, each beta particle is basically a high energy electron that has a 1 negative charge. The electron is not one of the original electrons from outside the nucleus, and it's produced by changing a neutron into a proton and an electron. So what happens, you have a neutron right here, and it breaks down into a proton plus an electron. That's beta decay. So what happens is, if you'll notice, the mass number doesn't change at all, but the atomic number goes up by 1 because you gain a proton. Protons and neutrons have the same mass, so your mass number doesn't change, but you gain a proton, so the atomic number increases. So here we have the example of uranium 239, and it breaks down into a beta particle and neptunium. Now, 239 is the same on each side, because 0 plus 239 equals 239. It's 92 total on the left side. A beta particle has a charge of a -1 plus 93 in neptunium, and that gives us 92. Remember, law of conservation. We have to have equal numbers on both sides. They can be rearranged, they can change form from one thing to another, but we have to keep it equal. So this, you have math, but it's simple math. This was always everybody's favorite unit. Now, a gamma ray is a high energy form of electromagnetic radiation. It doesn't have mass, it doesn't have charge. Because of its high energy and penetrating ability, the gamma radiation can cause great harm to living cells. It's the most dangerous of the three. So whenever you think of nuclear radiation, you're thinking of the gamma radiation. Now, they can pass easily through most types of material, and they require thick blocks of lead or extremely thick blocks of concrete to prevent them from passing through. You only have energy being released during gamma decay, so it doesn't affect mass number or the atomic number. Back during the Cold War, people were building bunkers, and some of the old houses you can still find bunkers that are very thick blocks of concrete. I was in New York City on Governor's Island, and they had all these signs posted, and I hadn't noticed it, but it was like this, and then it said fallout shelter. And my children, who are younger, they were like, Mom, why does it show that radioactive symbol? And so we had to go into what was happening decades ago, and that these signs were just remnants that nobody cared to take down. And it was just part of history now. So if we look at the electromagnetic spectrum, you can see where gamma rays fall. They have the shortest wavelength. If your wavelength, remember, as wavelength decreases, your energy increases. So if you have all that energy and you're absorbing it, it's going to cause damage to you. So gamma rays are very dangerous. That's what you'll get with that's what you think of whenever you think of nuclear radiation and cancer. Primarily, it's from gamma rays, but alpha and beta particles can also do that. Now, gamma decay generally doesn't occur alone, but it accompanies other modes of decay. Here we have uranium-238 going to thallium-234, and you could have alpha decay represented by the alpha symbol or the helium symbol. Either way, it's the same particle. It's both alpha particle. So beta rarely happens by itself. Usually it accompanies alpha decay or beta emission. You also have electron captures that occur. Now, alpha particles are the largest, and usually your skin is the easiest or is a protective barrier enough because you have 7 layers of skin. So alpha particles aren't going to harm you unless they get inside your body. If they get inside your body, they'll do extensive damage. Beta particles, you need a little bit more protection from beta particles. a half centimeter of lead. So a centimeter is about the width of your pinky. So you need lead that thick as a barrier. But gamma rays, you need 10 centimeters. 10 centimeters is about the diameter of probably a grapefruit. So you need lead that thick in order to stop gamma rays from coming towards you. So you need a barrier of 10 centimeters thick. All right, let's do some practice. And then I want you to check your answers. So first, let's look at this. What's the missing particle in this equation? So we have our uranium-238, atomic number 92, and 90 here. So we have to figure out the missing particle. So 238 minus 234 gives us 4. So this top particle is going to be 4. 92 minus 90 is 2. I'll show you the math so that you can follow it. Now, what particle has this atomic mass and atomic number? That would be your alpha particle, which is also your helium particle. Now, what is the product of the following beta decay? So we have 14 and 6 right here with our carbon. And we know that we're having beta decay, which is basically an electron. So 14 minus 0 is 14. So the mass number stays the same. 6 minus a minus 1 gives us 7. So we look at the periodic table and say, what has an atomic mass of 7? That would be nitrogen. So A would be the missing product. Now I want to come back up here for just a minute so that you can see this would be a neutron. Sometimes you have neutrons that are released during a nuclear decay. So if you ever see this symbol, that would be your neutron. Okay, let's look at 3. Complete the following reaction. Again, we have our radium, and it's 226 and 88, and it decays into radon-222. So now we have to determine what's missing. So 226 minus 222 is 4. 88 minus 86 gives us 2. So this is our alpha particle. If you have questions, let me know. We're going to do one more set of practice. I want you to try these on your own and then come back and we'll answer them and you check and see if you got them correct. So which of the following represents a nuclear fission reaction? Oh, we haven't gone over these yet, so we'll stop right there. I'll see you next time.